These are the answers to homework 5I. Here are the definitions I would like you to know. Now let's go to the questions. Number 1, using the standard heat of formations on handout 9, calculate the standard enthalpy change for the combustion of octane in kilojoules per gram of octane and for the combustion of ethanol in kilojoules per gram of ethanol. Then determine which fuel provides the most energy per gram. The one standard heat of formation that wasn't found on handout 9 was that for octane, and that was only found in table 6.2 of the textbook. So the first reaction we're going to do is the combustion of octane. And the balanced equation is 2 moles of octane plus 25 moles of oxygen yields 16 moles of carbon dioxide and 18 moles of water. If you were to look up from handout 9 and from table 6.2, the standard heat of formations for all the reactants and products, you would have found these numbers that are given here. To use standard heat of formations, we're going to take the standard heat of formations of the products and subtract the standard heat of formation of the reactants. That gives us a particular pathway to get the reactants to turn into the products. And because enthalpy is a state function, it doesn't matter what pathway we use to go from reactants to products, the enthalpy change will always be the same. So in this case, we're going to start on the product side. There are 16 moles of carbon dioxide, and we're going to multiply 16 moles multiplied by the standard heat of formation of carbon dioxide in kilojoules per mole. Then we're going to add 18 moles of water multiplied by the standard heat of formation of water. Now that we're done with the products, we'll move to the reactant side. We'll subtract 2 moles of octane multiplied by octane's standard heat of formation. And we'll subtract also 25 moles multiplied by 0 kilojoules per mole for oxygen. In the 4 terms in this calculation, the moles all cancel out. So we're combining kilojoules plus kilojoules minus kilojoules minus kilojoules. The answer will come out in just kilojoules. And with the 2 of the numbers being accurate to the ones column and 1 being accurate at the tenths column, when we add these together, we're going to round our answer to the ones column. So that comes out negative 10,114 kilojoules. This is the amount of heat released theoretically based upon the balanced equation at the top of the slide. And that equation says we are combusting 2 moles of octane. So this negative 10,114 kilojoules is the heat released per 2 moles of octane. If we wanted to convert this into kilojoules per gram, I will use octane's molar mass, and I will arrange it to make the moles cancel out. And now the units come out to be kilojoules per gram. So burning octane releases 44.259 kilojoules per each gram. Part B will do the same thing now for ethanol. When ethanol is combusted, the balanced equation is C2H5OH plus 3O2 yields 2CO2 plus 3H2O. Looking up data from handout 9, we have the standard heat of formations of each of the reactants and products. And the same technique we're going to use, heat of formation of products minus heat of formation of reactants. Starting on the product side, it's 2 moles of carbon dioxide multiplied by carbon dioxide standard heat of formation, plus 3 moles of water multiplied by the standard heat of formation of gaseous water, making sure we're looking up that one and not liquid water. Now we go to the reactant side, we subtract the heat of formation, so it's minus 1 mole multiplied by 278 kilojoules per mole for ethanol, and then minus 3 moles multiplied by the standard heat of formation of elemental oxygen, and because it's an element in its natural state on Earth at room temperature and room pressure, its value is 0. Once again, each of the 4 terms, the units of moles cancel out, so we're just adding together kilojoules, 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 and kilojoules. And 2 of the numbers here are only accurate to the ones place, so when we add them, we'll round our answer to the ones place. This comes out negative 1,235 kilojoules. This is the heat released for the balanced equation that we have written at the top of the slide. This is our theoretical value, and it's based theoretically on the combustion of 1 mole of ethanol. So we can say that this value is negative 1,235 kilojoules per 1 mole of ethanol. To convert it into kilojoules per gram, we'll just use ethanol's molar mass, arrange so the moles cancel out, and to 4 significant figures, this comes out negative 26.80. From these 2 answers, we can see that more energy is produced by the burning of 1 gram of octane than it is by burning 1 gram of ethanol, negative 44 to negative 26. So you actually get more energy from the octane than you do from the ethanol. We burn mostly octane in our cars here in the United States. If you were living in Brazil, Brazil grows a lot of sugar cane. They produce ethanol from the sugar cane, and all of their cars run on ethanol instead of octane. Because it doesn't produce as much energy per gram, therefore the mileage for all the cars in Brazil are not quite as good as the mileage here. And in fact, it even happens here to a certain extent because several months of the year, the state of California requires California gasoline stations to only use gas that has a specific percentage of ethanol in it. So at certain months of the year, we get extra ethanol placed into our tank to try to help with pollution. And if you notice at all, there are months during the year where your gas mileage goes down because you're trying to run your car on a less efficient fuel, the ethanol, instead of pure octane. Question number 2. Use standard heat of formations found on handout 9. Calculate the standard enthalpy change for each of the following reactions in kilojoules per gram of sodium. First reaction is the reaction of sodium with oxygen to form sodium oxide. We're going to use the standard heat of formations and go products minus reactants. So just looking up the values, starting on the product side, it's going to be 2 moles of sodium oxide multiplied by its standard heat of formation, which was negative 416. That's the only product. Now we go to the reactant side, minus 4 moles of sodium multiplied by its standard heat of formation. And Na solid is an element in its standard state at room temperature and room pressure on Earth, so its value is 0. Then minus 1 mole of oxygen multiplied by its standard heat of formation, also an element in its standard state at room temperature and room pressure on Earth, so its value is 0 as well. The 3 terms in this calculation all have the moles cancel out, so it's kilojoules minus kilojoules minus kilojoules, and the answer comes out to the ones column, negative 832 kilojoules. This is the amount of heat given off for the balanced equation we've written at the top, so it's our theoretical value, and we've calculated based on a theoretical number of 4 moles of sodium being reacted. So therefore, it's negative 832 kilojoules per 4 moles of sodium. Using sodium's molar mass, we can convert moles into grams, cancel out the moles, and we'll now have the energy released in kilojoules per gram of sodium. This comes out negative 9.05 kilojoules per gram of sodium. In B, we're doing the reaction of sodium with water, which we've seen in lab before. It's exothermic process. We would imagine this value to come out negative. A lot of heat and light were released. Using the standard heat of formations from handout 9, starting on the product side, we're going to go moles multiplied by the standard heat of formation of aqueous sodium hydroxide, which was given as negative 470. And all the values in that thermodynamic table are taken to at least be to the ones place. So even though there was not a decimal point in the number in the chart, we can assume it meant 470 with a decimal point, so 3 significant figures. That's the only product. Go to the reactant side. Oh, one more product, sorry, there's hydrogen. So plus 1 mole, oh, I put 2 there unfortunately, but that should be 1 mole of hydrogen multiplied by 0 kilojoules per mole. Now we go to the reactant side, minus 2 moles of sodium multiplied by 0 kilojoules per mole, and then minus 2 moles of liquid water multiplied by liquid water's standard heat of formation, which is negative 286 kilojoules. Which we assume 2 moles of sodium completely with negative 168 kilojoules per 2 sodium. Using sodium's molar mass, we convert them into grams. The units in kilojoules per gram. And so when sodium reacts with water, 8.00 kilojoules of heat energy are released per gram of sodium, so it's given as a negative number. C is the reaction between sodium and carbon dioxide. This balanced equation is 2Na plus CO2 yields Na2O plus CO. Products minus reactants, when we use our standard heat of formations, starting on the product side, there's 1 mole of sodium oxide multiplied by its standard heat of formation of negative 416 kilojoules per mole, plus 1 mole of carbon dioxide multiplied by its standard heat of formation of negative 110.5 kilojoules per mole. Over to the reactant side, minus 2 moles of sodium multiplied by its standard heat of formation, which is 0, and then minus 1 mole of carbon dioxide multiplied by its standard heat of formation, which is negative 393.5 kilojoules per mole. Moles cancel out in all four terms. The answer will be in kilojoules. And because one of the numbers here is only accurate to the ones place, our answer will have to be rounded to the ones place. I get negative 549 kilojoules. This is the theoretical amount of heat released when the balanced equation above that shows 2 moles of sodium having reacted with the carbon dioxide. So I can say it's negative 549 kilojoules per 2 moles of sodium. Using sodium's molar mass, we can convert this from kilojoules per mole into kilojoules per gram. And so when sodium reacts with carbon dioxide, it releases 11.9 kilojoules per gram of sodium. The final part of this question says, explain why a water or carbon dioxide fire extinguisher might not be effective in putting out a sodium fire. Well, the reason has to do with the fact that when sodium reacts with water, the process is exothermic. When sodium reacts with carbon dioxide, the process is exothermic. And if you want to prevent a fire, you have to break the fire triangle. And we're actually adding heat when you spray water or carbon dioxide onto sodium. And so because this is an exothermic reaction with either water or carbon dioxide, these types of fire extinguishers would not work to put out a sodium fire. Question number 3. The standard heat of combustion of butane gas, C4H10, is negative 49.52 kilojoules per gram of butane. Using the standard heat of formations on handout 9, calculate the standard heat of formation of butane gas. If you look at handout 9, there is no standard heat of formation of butane. That value is missing. This problem, we're going to try to calculate what it is, and we're going to do it because they've given us the heat of combustion of butane. That means the amount of heat released when butane burns. That reaction is butane plus oxygen yields CO2 and water. So this reaction balanced 2C4H10 plus 13O2 yields 8CO2 plus 10H2O. That's a combustion reaction, and that's the term or the value they gave us in the problem. They said its heat of combustion is negative 49.52, and they gave it into this form, kilojoules per gram, where they give you heats of reaction so that you can then use this number to calculate how much heat is absorbed or released in any particular process, depending upon what's in the denominator there, grams of C4H10, depending upon how many grams of C4H10 that you have actually burned. So if we want to use this number, I have to use my balanced equation at the top, which is saying that we're going to try to burn 2 moles of C4H10. So if that's moles of C4H10, and this conversion factor is kilojoules per gram of C4H10, I'm going to convert it from kilojoules per gram into kilojoules per mole with butane's molar mass. If I do that, the grams will cancel out, and I will now have the heat of combustion for butane in kilojoules per mole. And this is valuable to us now because we know we have a balanced chemical equation in which we're burning 2 moles of butane. So all I have to do is multiply this by the 2 moles of butane. The moles will cancel out, and we'll now know how much heat will be given off for the balanced equation at the top of this slide, which is showing that 2 moles of butane are being burned. To 4 significant figures, it comes out negative 5,758 kilojoules. So the reason this is important is because we know that number, negative 5,758, is the delta H for the reaction at the top of the slide. And the delta H of a reaction is related to the standard heat of formations of the reactants and products, arranged such that you go the standard heat of formation of products minus standard heat of formation of reactants. So the delta H naught for the above reaction, which is the negative 5,758, must equal 8 multiplied by the standard heat of formation of carbon dioxide plus 10 multiplied by the standard heat of formation of water minus 2 times the standard heat of formation of butane minus 13 multiplied by the standard heat of formation of oxygen. In this equation, I know every single variable, or at least I can look most of them up, except for the standard heat of formation of butane. This is the one we don't know right here. That's what we're solving for. The first number is the negative 5,758. We can look up the standard heat of formation of CO2, look up the standard heat of formation of H2O, and the standard heat of formation of oxygen is 0. So if I don't know this, that's the only variable in the equation, we can solve for it. So the heat of combustion for the balanced equation at the top, negative 5,758 kilojoules, will equal 8 moles multiplied by negative 393.5 kilojoules per mole, which is the standard heat of formation of carbon dioxide, plus 10 moles multiplied by the standard heat of formation of gaseous water, which is negative 242, then minus 2 moles multiplied by the standard heat of formation of butane, which we don't know, so I'm going to call that X, and then minus 13 moles multiplied by the standard heat of formation of oxygen, which is 0, and I'm just going to ignore that last term. So we're going to multiply out each of the terms on the right side now, and then we're going to try to simplify this. So the left side of the equation is negative 5,758 kilojoules. 8 multiplied by negative 393.5 comes out to be negative 3,148. 10 multiplied by negative 242 is negative 2,420. I then have minus 2 times x, and then 13 times 0 is 0. So if we take the two terms on the left side, the negative 3,000 and the negative 2,000, and move them over to the left side of the equation, I add all that up, the left side of the equation becomes negative 190.2 kilojoules, and that equals the negative 2 moles multiplied by x. If you divide both sides by negative 2 moles, you will get the units for standard heat of formations, which is always kilojoules per mole, and this turns out to be 95.1 kilojoules per mole as the standard heat of formation of butane gas.